Hey guys, it is Axiomatic Uncertainty here, and I'm back with another video. This time we are going over, yet another reinforcement slash deep Q learning project slash Q learning. Sorry, that's the dog. And this time we're going to be talking about this little project here. You can see it running on the screen, and this is the CartPole version 1 from OpenAI Gym. And I will go to the site just so you can see it. So I'll just open up a new tab, OpenAI's Gym site right here. And what you can see here is we have all these environments. So by default it was on classic control, however we could go to any of these. So let's say we go to the main page of the site. You can see that there are all of these, agents and games, right? And I chose to do a simple game just to figure out how to interface with the environment, and also to try out a new approach to machine learning that I wanted to check out, which is, the one which you're about to see. So CartPole is essentially a game of balancing a pole like this one, whose suspension is based upon an axis, or I guess a joint, moving through the side of a cart. And essentially the properties of this are that it can slide back and forth at a speed of -1 or +1. You can see that here. You can apply a force of either of those two things in order to accelerate or decelerate the cart. I guess it would just be accelerate in either direction. And essentially, it's a very simple design. However, the problem is, quite an interesting one. So, what I've decided to do for my approach to this problem is to write a deep Q network whose neural network is relatively large and capable of handling, four-dimensional input, which is what this game gives us. It gives us, sorry, the dog is being very loud. It gives us, x, x prime, theta, and theta prime. X prime being the velocity on the x-axis, x being the location on the x-axis, theta being the angle of the pole relative to the horizontal axis, or the axis of the cart. And then theta prime being, as with x prime, the relative change in the angle, per unit of time, aka per frame of the game. So that's essentially all of the technical details of the scene. Now, getting into the model itself, what are we doing? First, we have to import Gym. So OpenAI has their own library. It's called Gym. If you want to install it, all you have to do is open up command prompt. Sorry, the dog's being a bit loud again. And run pip install and then Gym. I already have that. However, that's all you need to do in order to get it onto your system. As long as you have pip and you're running, I think Python 3 and above will work just fine. That's what I'm using. I'm running 3.7 right now. So basically, we do that, and then we import, standard stuff for reinforcement learning and machine learning in general. We're using Keras for this one. There's no need to use TensorFlow since the model is not that dynamic or complex. It's certainly, an easy thing to do, and so I don't see any point in doing anything else here. So, what are we doing, right? That's, an important thing here is that we're running essentially similar settings to the tic-tac-toe AI. We are using os.path here, so basically what this does is when we define our model, we can use os.path in order to check if the file exists. If the file does exist, we override this compiled, randomized model, with our current weights and biases of the pre-existing model, and then notify the user that that model has been detected. Now, we only have one real function that we needed to define here, and that is the process data function. All this does is it takes in our data and generates a reward vector. And the way I'm doing this is a bit different from what most people would use. The way I've chosen to do this all is that the value will be chosen essentially through this strange function. Now, one thing I did change from before is that instead of just using a numpy array of zeros, we are using a numpy array whose alternate, like, the value that wasn't actually our action is just the predicted value, so that we don't change anything when we're running between states. With the tic-tac-toe script, we were using a numpy array of zeros because we wanted to be able to at least like normalize our values to something and to keep them small. Typically, I didn't want all of our values to get extremely large, since deep Q learning can sometimes be relatively unstable in terms of Q values and rewards, and I wanted them to be clearly disparate in the later stages of the model. So that is a different scenario. Here we're not doing that anymore, and you'll notice our rewards are all negative because the way I see it, there are a couple of approaches that can be taken to this game, and I think that mine is just good in that it works. So what do I mean by this being negative all the time? Well, the only thing that is actually being changed here is how negative the value is. So the further separated we are from the end game state, the less negative the value is. So theoretically, if the game lasts forever, this value here will be a 0, which is our ideal value. The higher the value, the better the result. And so the more that this thing plays, the better it's going to get. And so the longer the run, in terms of frame count, aka steps, the closer this value gets to 0 in theory, as long as it gets better. And so over time, it just converges to that, and that's why it has been working thus far, I believe. The only anomaly that I've noticed just now is this reward depreciation is greater than 0, or greater than 1, which still kind of baffles me. I haven't had time to think through why that would actually be working. The thing is, having a reward depreciation that's greater than 0 suggests that the actions at the beginning of the process are actually the actions which are, overall worst. And that's kind of strange, That suggests that the actions that need the most correction are the initial actions as opposed to the end actions. And it also means that the longer the thing runs, the more negative the value. So I'm not really sure what's going on there. I think what's happened here is that this reward depreciation has not actually affected the gameplay. I had it at a lower value, and I believe what happened is I changed this after I started running it, which would explain that. I'm going to do further testing in order to attempt to figure out what's happening. But, until then, we're just going to ignore that and assume that I'm correct in that it's below 1, since before when I tested it, it was working with it below 1 as well. So next, we're going to talk about this, process data. We already talked about that, so we're going to talk about this stuff. So first off, it has 2 modes, training and demonstration. If the mode is not training, we want our epsilon greedy value to be very low. The only reason I have an epsilon greedy at all is that the games are dynamic. So you can see this game, right? It ran poorly. However, this game is running very well. So it just creates dynamic games so that they're not all the same when it's running, or at least nearly the same. I know, the system does, the system being OpenAI Gym, does introduce random step counts where, like, if I step once, it may actually run that same step, 1, 2, 3, 4, 5 times, and you can't predict that, and that's supposed to create, more generalized models and sort of force them to behave that way with, games that are actually training, like, to run in real time as opposed to, like, being board games or something like that. So I think that's interesting. But, keeping it higher just creates more dynamic games for the user to watch, even though it's not necessary when we're not training. Right. The episodes, basically what we do here is we start a while loop after that. We're printing out epsilon greedy each time because we have a decay factor now for our, e greedy value. Each time we're decreasing it by 0.1, I believe. I don't remember where I put that. Yeah, so it decreases. And then we're running 50 episodes, aka 50 games. So whenever a game ends, we just, when essentially the software automatically makes this done variable equal to true. And so this loop is broken then, and then we just increment this total variable by the score, which is the number of frames that it survived that time. Basically what the total does is allows us to calculate the average number of frames, especially since that helps us find a benchmark, since originally when they had version 0 online, you were able to submit your scores, and I believe, if I remember correctly, the benchmark for actually having solved the game, I have air quotes which you can't see, solved being, it can still be unstable, but, for all intents and purposes, making it 200 frames is significant enough to say that it has nearly, solved it, and it would just take more training to get there, but it will get there, and it proves that your algorithm is, viable. So, basically, in order to solve it, you have to make it to 200, or maybe it's like 190 frames on average for a series of trials. I don't remember how many that is. Mine has broken that by quite a bit. I think it's at like 250 after maybe 20 to 30 minutes of training. So it's pretty good. I'd say there were more efficient ways to do this stuff, but it worked, and it didn't take that long to set up. I think I started doing this last night at like 11 o'clock maybe. Did some work on it this morning after a seminar at the library, and it's gone pretty well. So additionally, there's some functions here for saving things to memory, randomizing orders. Oh, oops, let me just put that back. And whatnot. And that's about it, pretty simple system. Very, very simple. It only came out to 113 lines. One thing to note, if you're going to try this, you do need to do something important here, which is after you close your environment, you're going to want to also delete it. What I found was that deleting this, not having any point at which this environment is deleted, during your program's runtime, caused this crash for some reason whenever a loop was completed. I don't know if there's another workaround, but just restarting the environment, reinitializing, when I reinitialize the neural network, actually seems to work as like a nice hotfix for that. So deleting the environment after I close it seems to work. The one thing I did notice is that the environment, if you do, environment.close, it continues to run in the background, which I find to be peculiar, since from what I've seen in the documentation and from other users is that .close is supposed to denote the termination of the process, but that's just my observation. Additionally, one more thing that you should know is that I'm training on a low epic count. I believe that's how you pronounce that. And the reason for that, maybe it's epoch, I don't know. The reason for that is, we don't really want to overfit like specific sequences. Like if we had one really bad run amongst, a series of good runs, then we may overwrite a lot of our progress by, putting too much emphasis on that one run, and so I've decreased that value to 1 and run, instead relatively large episode counts. And as you can see, if I just open this up, we're averaging, above 200, so you can see this runs 272, 268, 246, 225, and if you watch it actually play, it does seem to have a good grasp on, how stabilization works. You can see sometimes it does better than others, so this one is very, very good. However, so this one is where this is what I've been noticing, is like, so it hasn't perfectly learned it. It's clearly unstable in that, even if it does fail, or even if it does work, I should say, it eventually reaches a point at which this, like, I guess you could call it, like, dynamic equilibrium between, the pole's balance and its position on the screen, falls out of, order, and essentially we see it start to slide to the right, and then in order to compensate for that, it begins shaking back and forth further, and then the pole becomes, unstable, and eventually hits, it either hits the edge or the pole shifts too far left or right, and that theta value triggers an end to the episode. So that's one interesting thing. I think given more training time, it could reach the thousands, but, we'll have to see. I may update on the tic-tac-toe and CartPole in the future, talking about some more, research into how changing the structures affects results. But, for now, that's going to be me signing out. Bye.